Hey everyone, and welcome back for another deep dive. Today, we're going to be looking at F1.
F1.
This is a database system
Yeah.
developed at Google, and we're going to be taking a look at two different papers. Actually, one on F1 and one on Spanner,
Right.
which is the underlying technology that F1 is built upon.
Yeah. So F1 is really interesting because it's kind of a hybrid database.
Oh, okay.
It's like it takes the best of both worlds.
Like a mule or something.
Yeah, like a filial one, a hybrid in genetics.
Okay.
And it tries to combine two sort of seemingly opposite approaches to database design.
Okay.
And that is the massive scalability and availability of NoSQL systems with the consistency and usability of traditional SQL databases.
Okay, so before we jump into the specifics of how it actually accomplishes that,
Sure.
can you set the scene a little bit? Like, why was Google developing this? What problem were they trying to solve?
Yeah, so this was developed to support Google's AdWords business.
Uh-huh.
And so, AdWords is like a massive global system,
All right.
and it has to be up and running pretty much 24/7.
Sure.
So it needs to be highly scalable and reliable.
Yeah. Any downtime for AdWords would be a major financial hit
Absolutely.
to Google.
Huge, 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 huge.
Yeah, so they need something that's going to be rock solid.
So the initial implementation of AdWords actually ran on a sharded MySQL database.
Okay.
And sharding basically means, taking your data and you're breaking it up into smaller chunks,
Right.
and you put those chunks on different servers.
Okay.
And so that worked well for a while.
Mm.
But as AdWords grew,
Yeah.
they started hitting the limits of what MySQL could do,
Okay.
both in terms of just the volume of data
Right.
and the need for really strong consistency and reliability guarantees.
Okay, so they needed to come up with something new.
Exactly.
Right, so then F1 was born.
Yeah. So it's not just F1, though.
Okay.
So F1 relies heavily on this other system called Spanner.
Okay.
And Spanner really handles a lot of the heavy lifting in terms of things like data storage, replication fault tolerance, and importantly, it handles synchronous replication across data centers.
Okay, so
Yeah.
so just real quick, when you say synchronous replication, does that mean like the data is being copied over in real time
Yeah,
as it's being updated?
exactly. So it's like being mirrored across multiple locations at the same time.
Okay.
And this ensures consistency of data, which is really, really important for a system like AdWords.
Right, because if you had like a delayed replication, you could end up with conflicts and all sorts of problems.
Exactly. Yeah, you can have all sorts of weird anomalies.
Yeah.
But this comes at the cost of latency.
Right, because you're waiting for that confirmation from every data center.
Right. You have to wait for everybody to kind of get on the same page before you can say, okay, we're done with this operation.
Got it.
So there are trade-offs there, but we'll get into those a little bit later.
Yeah, I was going to say, so if we're talking about a massive system like AdWords
Right.
and all the data it handles, wouldn't that synchronous replication introduce a lot of lag?
Yeah, it can.
Okay.
So F1 has some clever tricks to try to minimize that impact.
Okay.
And I will dive into those later on, but just keep in mind that Spanner really makes sure that all copies of the data are always in sync.
Okay, so it sets the stage for that rock-solid reliability
Exactly.
that they're looking for.
It's the foundation.
Got it. All right, so we've talked a little bit about Spanner and its role,
Right.
but what about F1 itself? How does it make things more efficient? What are some of its key innovations?
Yeah, so one of the key innovations in F1 is its data model.
Okay.
And they use a hierarchical data model.
Okay.
It's kind of like a family tree,
Right.
where you have parent tables and child tables nested within them.
So instead of the data being scattered all over the place,
Yeah.
it's grouped together based on relationships.
Right, so it's all nicely organized.
Okay.
And this is particularly useful in a distributed setting.
Right. I could see how that would help in a system like F1.
Yeah, so for example, if you think about the AdWords schema, you might have a customer table at the top level,
Mm-hmm.
and then nested within each customer, you would have a campaign table.
Okay.
And then nested within each campaign, you'd have an ad group table,
I'm following you.
and so on.
So all the data relating to like a specific customer is actually stored together?
Yeah, it's all clustered together physically.
That's smart.
And this makes it really fast to do a lot of common queries and transactions.
Yeah, it's like keeping all the files for a project in the same folder instead of having them scattered across your computer.
Right.
Makes it much easier to find things.
So this hierarchical clustering really speeds things up,
Okay, that makes sense.
especially when you have a database that's distributed across multiple servers and data centers like F1.
Okay, cool. So another thing that was mentioned in the paper is this idea of protocol buffers.
Protocol buffer.
Could you explain what those are and how they fit into F1?
Yeah, so protocol buffers are like a way to define structured data types.
Okay.
You can think of them like a flexible container for data. And one of the benefits of using protocol buffers is that it eliminates this need for data conversion between the database
Okay.
and your application.
So you don't have to worry about translating data back and forth.
Exactly. You don't have to translate between different formats.
Got it.
So that's a huge time saver for developers.
Okay, cool.
And another benefit is that protocol buffers have this feature called repeated fields.
Okay.
And repeated fields can act like little mini tables nested inside a table.
So it's like having a table within a table.
Right.
Yeah.
So this can be really useful for optimizing storage and retrieval for certain types of data.
So it's almost like it allows you to customize the structure of the data even further.
Yeah, exactly. It gives you a lot of flexibility.
Okay, that's cool.
So yeah, it's a really powerful tool.
All right, so we've got this data that's structured in a hierarchy.
Yeah.
We've got these protocol buffers that give us flexibility.
Right.
But how do you actually search through all this data? What kind of indexing does F1 use?
Yeah, so F1 supports both local indexes and global indexes.
Okay.
And each of these has its own trade-offs. So local indexes are really fast,
Okay.
but they're only limited to searching within a single, what they call a root entity,
Okay.
like a particular customer or a particular campaign.
Okay, so if you need to search across the entire database,
Right.
then a local index is not going to cut it.
Exactly.
Okay.
So for that, you need global indexes.
Got it.
Global indexes are more powerful in terms of their search capabilities, but they can be more expensive to maintain, especially for updates.
Okay, so it's a trade-off
Yeah.
between speed
Yeah.
and scope.
Exactly.
Got it.
So choosing between those two really depends on the needs of your application.
Okay, that makes sense.
It's all about picking the right tool for the job.
Cool. All right, so let's say you need to make a change to the structure of the database.
Yeah.
Like you need to add a new column to a table or something. How does F1 handle that? Because in a lot of database systems, that would require taking the database offline,
Right.
which is obviously a big no-no for a system like AdWords
Yeah, absolutely.
that needs to be up and running all the time.
So this is where F1's flexibility really shines.
Okay.
It allows you to make schema changes like adding a column without taking the database offline.
Wait, how is that even possible?
Yeah, it's pretty complex.
Especially with data being replicated across multiple servers.
Right.
You'd think that would create a lot of problems.
So they use a multi-phased approach
Okay.
to make sure that everything stays consistent, even if different servers are temporarily running different versions of the schema during this update process.
Got it.
So it's a really clever system.
So they figured out how to like swap out the engine
Yeah,
while the car is still running.
exactly. It's like a live performance where you're
Yeah.
changing the set behind the scenes while the show is still going on.
It's pretty impressive.
Yeah, it's some serious engineering.
All right, so we've talked about how F1 structures data,
Yeah.
how it handles searching, and how it even allows for schema changes on the fly.
Right.
But what about the different ways that developers can actually interact with the database? What kinds of transactions does F1 support?
Yeah, so F1 offers three main types of transactions.
Okay.
You have snapshot transactions,
Okay.
pessimistic transactions, and optimistic transactions.
Yeah. All right, so let's break those down.
Sure.
What are snapshot transactions all about?
So snapshot transactions are really good when you need a consistent view of the data at a particular point in time.
Okay.
So it's kind of like taking a picture of the database.
Take a snapshot in time.
Exactly.
Wow.
And this is really useful for things like generating reports or running analytics where you don't want the data to be changing underneath you while you're working with it.
It's like freezing the data.
Yeah,
So
exactly.
you can get a consistent view.
Right.
All right, what about pessimistic transactions?
So pessimistic transactions are a little bit more traditional.
Okay.
They use a locking mechanism to prevent conflicts
Okay.
when you have multiple users trying to update the same data.
So it's like putting a do not disturb sign on the data.
Exactly. Well, you're working on it. So it guarantees that you're not going to have any conflicts.
Right.
But it can be a little bit slower because of all this coordination that needs to happen.
So it's a trade-off between speed and data integrity.
Exactly.
Okay, and lastly, what about optimistic transactions?
So optimistic transactions are kind of the speed demons.
Okay.
They assume that conflicts are going to be rare,
Uh-huh.
and so they proceed without doing any locking.
Okay.
So this makes them really fast.
Uh-huh.
But if a conflict does occur, the transaction has to be rolled back
Oh,
and then retried.
So it's like you're just hoping for the best.
Right.
And if something goes wrong, you just start over. Okay, so it's another trade-off between speed and the potential for having to retry the operation.
Exactly.
Interesting.
So it really depends on the application and how much risk you're willing to take.
Right. Okay, so you've got these 3 different transaction types.
Right.
Which give developers flexibility in how they interact with the database.
Exactly.
And then there's this other feature that I found fascinating, this built-in change history.
Yeah.
What is that all about?
So every change that's made to the database is automatically tracked and logged by F1.
So you have a complete history of all the changes.
Right. You have before and after values for every row of data.
Wow. That's like having a time machine for your data.
It is.
That's really cool.
Yeah. It's a pretty powerful feature.
So it's not just for auditing purposes.
Right.
Like you can actually use this change history to do some really interesting things with your applications.
Yeah, exactly. So you can imagine building applications that need to be notified when specific data changes. Or you could use it to build a caching system that's really efficient.
Yeah. Or even like a system that could react to changes in the data in real time.
Exactly.
That's awesome.
So it opens up a lot of possibilities.
Okay, so we've talked about the data model.
Yeah.
The protocol buffers the indexing, the schema changes the transaction types, and the change history.
Yeah.
But how does all of this come together in practice? What can you tell us about the AdWords case study?
Yeah, so AdWords is really the poster child for F1.
Okay.
It's a massive system, as we've talked about.
Right, billions of updates every day.
Yeah, billions of updates per day, trillions of rows of data.
It's hard to even fathom that scale.
Yeah, it's mind-boggling.
Yeah.
And one of the biggest things that AdWords needs is high availability.
Of course, any downtime is going to cost them a ton of money.
Absolutely, yeah, because they're losing revenue.
Yeah.
Every minute that the system is down.
So they need to be up and running as much as possible.
Exactly.
Okay, so how has Spanner actually helped them achieve that?
So with Spanner, they've been able to achieve what they call 5 nines availability.
5 nines? What does that even mean?
So 5 nines means that the system is operational 99.999% of the time.
That's incredible.
Yeah, it's pretty amazing.
How do they do that?
So it's really a combination of a couple of things.
Okay.
So first of all, you have the distributed design of Spanner. So remember how we talked about how it replicates data across multiple data centers?
Right, it's a global safety net.
Exactly.
For their data.
So if one data center goes down, the other data centers can seamlessly pick up the slack.
So it's like having multiple engines on an airplane.
Yeah.
If one fails, the others keep it in the air?
Exactly.
Okay, so that's one part of it.
Right.
But what about performance?
Yeah.
Because we talked about how synchronous replication can sometimes introduce latency.
Right.
So how do they balance those two things?
So it turns out that the latency introduced by synchronous replication is often counterbalanced by performance gains elsewhere. So remember how we talked about the hierarchical data model in F1?
Right.
And how it keeps related data clustered together?
Yeah, that reduces the need to hop between servers to find the data you need.
Exactly.
Okay.
And so that actually speeds things up quite a bit.
Got it.
And then the F1 client library also plays a role.
Yeah.
It has a simplified ORM layer that helps developers avoid some common pitfalls that can create performance bottlenecks in distributed systems.
So it's like a set of guardrails.
Yeah, exactly.
Keep developers from accidentally shooting themselves in the foot.
Right. It encourages good coding practices.
Okay, that makes sense.
And so the end result is that even though AdWords is running on this distributed database system that's spread across multiple data centers, its performance is actually comparable to or even better than its previous single server setup.
So they're getting all the benefits of scalability and reliability without sacrificing performance.
Yeah.
That's amazing.
It's pretty remarkable.
All right, so we've seen how Spanner can achieve these incredible levels of availability.
Yeah.
But how does it actually ensure that everything stays consistent across those multiple data centers? How do they agree on what happened first when operations might be happening in different locations potentially at the same time?
Right, so that's where TrueTime comes in.
Okay, this is the part I've been waiting for.
Yeah, this is a really cool part.
Tell me all about TrueTime.
So TrueTime is this globally consistent clock system.
Okay.
And it's kind of like a revolution in how we think about time in a distributed environment.
All right. I'm intrigued.
So most clocks just tell you the time right.
Yeah.
TrueTime actually provides bounds on its own uncertainty.
Okay, so it knows how much it doesn't know.
Exactly.
Yeah.
That's wild. It's kind of like saying it's 3:15 p.m., but I'm 99.99% certain that it's somewhere between 3.14.59 and 3.15.01.
So it's got like a little margin of error.
Right.
But it's aware of that margin of error.
Exactly.
And it uses that to keep things in sync.
Right. So because TrueTime can quantify this uncertainty, Spanner can use it to guarantee that all transactions, even if they happen in different data centers, appear to occur in this globally agreed upon order.
Okay, so even if two transactions happen in two different data centers at almost the same time, TrueTime can figure out which one actually came first.
Exactly. It's
Yep.
like having this ultimate arbiter of time that everybody trusts.
That's really cool.
Yeah, it's a pretty ingenious system.
So TrueTime is like the conductor of the orchestra,
Yeah,
making sure everyone's playing in sync.
exactly.
Okay, I think I need a moment to process all of this.
Yeah, it's a lot to take in.
We've covered so much ground already,
We have.
but we're just getting started.
I know, we've only scratched the surface.
Yeah, so when we come back,
Yes.
we're going to dive even deeper
Right.
into Spanner's architecture
Yes.
and explore how it actually achieves all of these incredible feats,
Exactly.
all thanks to TrueTime.
TrueTime is the key.
All right, sounds good. I'll see you in part 2.
All right, see you then.
All right, welcome back. So last time we left off talking about TrueTime and how it keeps everything in sync across these different data centers.
Right.
But can we take a step back and talk about how Spanner actually spreads this data across these data centers?
Sure, yeah.
Like it can't just be a simple backup, can it?
No, it's much more sophisticated than that.
Okay.
So Spanner's architecture is built around these things called zones.
Okay.
And you can think of a zone as kind of a cluster of servers that all work together
Okay.
to manage a portion of the data.
So it's like having multiple mini databases
Yeah,
that are all carefully coordinated.
exactly.
Wow.
And then within each zone, you have these even smaller units called tablets.
Okay.
And these are the individual chunks of data that get distributed.
Okay.
And each tablet is then replicated across multiple servers
Okay. I'm following you.
using this algorithm called Paxos.
Paxos, yeah, that rings a bell.
Yeah,
That was mentioned in the paper.
it's like a consensus building mechanism for the replicas.
Right? So it makes sure that all the replicas of a tablet agree on the same state,
Exactly.
even if some of the servers fail.
Right.
Okay, so it's all about redundancy,
Yeah,
making sure the system can handle failures gracefully.
exactly. If one server goes down, the others can pick up the slack without missing a beat.
Okay, but it sounds like Spanner goes even further than just replicating individual pieces of data
Yeah.
with this concept of directories.
Right. So directories in Spanner
Okay.
are a way to group related data together,
Yeah.
even if that data spans multiple tablets.
So it's like keeping all the files for a specific project in the same folder,
Right, exactly.
even if they're physically stored on different hard drives.
Exactly.
Okay, so it's about keeping related data together for efficiency.
Right.
Okay.
And the cool thing about directories is that Spanner can actually move directories between zones automatically
Oh, wow.
to optimize performance or to keep data close to where it's needed most.
So it's like Spanner is constantly rearranging the furniture.
Yeah.
To make sure everything is in the right place.
Exactly. It's like a self-organizing system.
That's really cool.
Yeah.
So this dynamic data placement is one of the keys to Spanner scalability.
Right. It allows it to handle these massive workloads
Okay, that makes sense.
and adjust to changing demands.
Now, I'm curious about how Spanner actually handles transactions in this complex setup,
Yeah.
especially with those different types of transactions that we talked about.
Right. Right.
Snapshot, pessimistic, and optimistic.
So Spanner's transaction management is really tightly integrated with its replication mechanism.
Okay.
So remember those Paxos replicas we talked about?
Yeah, the synchronized clones of the data.
Exactly.
Okay.
So for read-write transactions, which are kind of the most common type,
Uh-huh.
Spanner uses a two-phase locking approach.
Okay.
So the first phase involves acquiring locks on all the data that needs to be updated.
So it's like saying, hey, I'm working on this data. Don't let anyone else touch it
Right, exactly.
until I'm done.
So you prevent conflicts while the transaction is in progress.
Got it.
And once all the locks are acquired, the transaction can go ahead and make the changes.
Okay, and then what happens?
So once the changes are made, the transaction enters the second phase,
Okay.
which is called the commit phase.
Mm-hmm.
And this is where TrueTime comes in.
TrueTime always showing up at the crucial moment.
Right. TrueTime is essential here.
Okay.
So TrueTime assigns a globally consistent timestamp to the transaction.
Okay.
And this timestamp indicates the exact point in time when the transaction was committed.
Okay.
And because TrueTime is globally consistent, this timestamp is guaranteed to be unique and correctly ordered, no matter where the transaction occurred.
So even if two transactions are committed in different data centers, like almost simultaneously,
Right.
TrueTime can still figure out which one happened first.
Exactly.
Okay.
And this precise ordering is essential for maintaining data consistency and ensuring that all the replicas converge to the same state,
Got it.
reflecting the correct order of operations.
That makes perfect sense for read-write transactions.
Right.
But what about snapshot transactions?
Yeah.
They're only reading the data, not changing it, right?
Right. So snapshot transactions are a lot simpler
Okay.
because there are no data modifications involved.
Okay.
So all you're doing is capturing a snapshot of the database at a specific moment in time.
And how is that moment determined?
So the client can provide a timestamp
Okay.
or a staleness bound,
Okay.
and Spanner will select the appropriate snapshot.
So it's like saying, show me the database as it looked 5 minutes ago.
Right, exactly.
Or show me the most recent snapshot that's no more than 10 seconds old.
Exactly.
Yeah.
And thanks to TrueTime's consistency guarantees the snapshot is always accurate and reflects a consistent view of the data at that specific point in time.
It's just like a built-in time machine for your data.
It is, yeah.
That's really neat.
Yeah, it's a powerful feature.
But what about optimistic transactions?
Right.
The ones that assume that conflicts are unlikely?
Yeah, so optimistic transactions are handled a bit differently. They
Right.
proceed without acquiring any locks,
Okay.
which makes them faster.
Uh-huh.
But it also means that there's a risk of running into conflicts.
Right. That trade-off between speed
Yeah,
and the potential for having to roll back and retry the operation.
exactly.
So how does Spanner handle that?
So Spanner uses this clever mechanism to detect conflicts in optimistic transactions.
Okay.
So each row of data has a timestamp associated with it
Okay.
that indicates when it was last modified.
So it's like keeping track of the last updated date for each data entry.
Right, exactly.
Okay.
And when an optimistic transaction reads some data,
Uh-huh.
it records these timestamps.
Okay.
And if the transaction later tries to commit some changes,
Uh-huh.
and it detects that any of the data that it read has been modified since it was read.
Then it knows there's a conflict.
Exactly.
All right.
And in that case, the transaction is aborted and has to be retried.
So it's like a safety mechanism to make sure that optimistic transactions don't accidentally corrupt the data,
Exactly.
even though they're not using locks.
Right.
Okay, that's really clever.
It's a really elegant solution.
So we've talked about how Spanner replicates data,
Yeah.
how it handles transactions.
Right.
But there's one more piece of the puzzle that I'm curious about,
Okay.
and that's schema changes.
Right.
Because we talked about how Spanner manages to do those without any downtime.
Yeah.
And that seems like a huge challenge in a distributed database.
It is definitely a challenge.
So how do they pull that off?
So Spanner uses a special type of transaction
Okay.
called a schema change transaction.
Okay, so this is a transaction that's specifically for changing the structure of the database.
Right, not just updating the data within it.
Okay.
And the key thing about schema change transactions
Uh-huh.
is that they're non-blocking.
Okay.
So they don't acquire locks
Okay.
like regular transactions do.
Got it.
So they don't interfere with other operations that might be happening concurrently.
So they can run in the background while other things are going on.
Exactly.
That's cool.
And instead of using locks, Spanner leverages TrueTime to assign a timestamp to the schema change transaction.
Do TrueTime again.
Right,
Always there to keep things in order.
exactly.
Okay.
And this timestamp is registered with all the replicas,
Mm-hmm.
and any reads or writes that depend on the schema are synchronized with this timestamp.
Okay, so if a read or write happens before the schema change timestamp, it can proceed as normal,
Right,
but if it happens after, it has to wait.
exactly.
Okay.
And this allows Spanner to gradually roll out these schema changes across all the replicas
Got it.
without causing any disruptions or inconsistencies.
That's an incredibly clever solution.
It is, yeah.
It's like doing open heart surgery while the patient is still running a marathon.
Right, it's pretty amazing.
So Spanner can handle these really complex operations
Yeah,
in a distributed environment without compromising performance or reliability.
right. It's a testament to the careful design and engineering that went into the system.
Okay, my mind is officially blown.
I know, it's
What?
a lot to take in.
I need a moment to digest all of this.
Yeah, let's take a break.
And when we come back, we'll talk about some real-world examples of Spanner in action.
Sounds good.
All right, welcome back to our deep dive into Spanner and F1. So we spent the last two parts really digging into the technical details.
Yeah, on the nitty-gritty.
But now I kind of want to connect all that back to the real world
Sure.
and see how these innovations actually translate into benefits. So let's revisit the AdWords case study.
Yeah.
Could you tell us a little bit about how Spanner has actually improved things for Google?
Yeah, absolutely. So, as we talked about, AdWords is this massive system, right?
Right. Billions of updates.
Billions of updates every single day. Trillions of rows of data.
Yeah, it's mind-boggling.
Right. And one of the biggest challenges for AdWords, even before Spanner, was achieving high availability.
Of course, because any downtime means
Lost revenue.
Lost revenue, frustrated customers.
Absolutely. So it's the heart of Google's advertising business.
Right. It's their cash cow.
It needs to be up and running reliably.
So reliability is paramount.
Absolutely. And with Spanner, they've actually managed to achieve 5 nines availability.
5 nines. That's incredible.
Yeah, so that means the system is operational 99.999% of the time.
So it's practically never down.
Pretty much never down.
How do they manage that?
So it's a combination of things.
Okay.
But the foundation is really Spanner's distributed design. And its use of synchronous replication across those multiple data centers.
Right. So we talked about how each tablet of data is replicated across multiple servers.
Exactly.
And then those servers are spread out geographically.
Right, all over the world.
So it's like having a safety net woven from data centers.
Yeah.
If one goes down,
The others can pick up the slack.
seamlessly.
Yeah. And because the replication is synchronous, all those replicas are constantly being updated. So even in a failure, no data is lost.
So it's like having multiple engines on an airplane. If one fails, the others can keep it in the air.
Exactly. That kind of fault tolerance is crucial for a system as critical as AdWords.
Okay, so that explains the reliability. But what about performance?
Yeah.
Didn't we say that synchronous replication could introduce some latency?
It can. It can introduce some latency. But it turns out that the latency introduced by synchronous replication is often counterbalanced by performance gains elsewhere.
Okay, so where are they getting those performance gains?
So remember we talked about F1's hierarchical data model?
Yeah.
And how it keeps related data clustered together.
Right, that reduces the need to hop between servers to find the data you need.
Exactly. And that can really speed things up.
Okay.
And then the F1 client library also plays a role. It has that simplified ORM layer that helps developers avoid bad practices.
Right, like those guardrails we talked about.
Exactly.
And prevent them from shooting themselves in the foot.
Yeah. And so the end result is that even though AdWords is running on this distributed database system across multiple data centers, its performance is actually comparable or even better than its previous single server setup.
So they're getting the scalability and the reliability without sacrificing performance.
It's pretty amazing.
That's incredible.
It really is. It's a testament to the innovation behind Spanner.
So we've seen the technical marvels of Spanner.
Yeah.
But I'm also kind of curious about the human side of things.
Sure.
What were some of the key lessons learned from building and operating such a groundbreaking system?
That's a good question. One of the biggest takeaways was the importance of simplicity.
Okay.
So while Spanner's internal workings are incredibly complex,
Right.
the interface that developers interact with is designed to be relatively straightforward and intuitive.
So it's like a really powerful engine.
Yeah.
Hidden beneath a user-friendly dashboard.
Exactly. And this focus on simplicity has made Spanner much easier to adopt and work with.
Right, because if it's too complicated,
Yeah, developers are going to shy away.
nobody's going to want to use it.
Exactly.
Makes sense.
Another key lesson was the power of automation.
Okay.
So Spanner automates many of the complex tasks associated with managing a distributed database, things like data placement replication failover.
So it's like having a self-driving database.
Yeah.
That takes care of all the low-level details.
Exactly. So it frees up the developers to focus on the bigger picture.
That's pretty cool.
Mhm.
Anything else that surprised the team?
I think another big one was the importance of thorough testing.
Okay.
They invested heavily in creating a comprehensive test suite to make sure that Spanner was rock solid.
Right, because this is mission-critical stuff.
Absolutely. If Spanner goes down,
Google goes down.
yeah, there are major problems.
So they had to make sure it was bulletproof.
Exactly. And that investment in testing really paid off. Spanner has proven to be incredibly reliable and robust in practice.
Wow. This has been an incredible deep dive.
Yeah, it's been fun.
I feel like we've only scratched the surface.
Yeah, there's so much more we could talk about.
But we've covered a lot of ground. We've seen how Spanner combines the scalability and availability of NoSQL systems
Right.
with the consistency and usability of traditional SQL databases.
It's a hybrid system that's really pushing the boundaries.
And we've seen how it's actually being used in a real-world setting
Yeah,
at massive scale to power one of Google's most important products.
absolutely.
So yeah, I'm incredibly impressed by what Google has accomplished with Spanner.
Yeah, it's a game changer.
It makes you wonder what other challenges they'll be able to tackle with this technology in the future.
No doubt they're already working on the next big thing.
Well, on that note, I think we've reached the bottom of this deep dive.
I think so.
Thanks for joining us. It's been an absolute pleasure exploring Spanner and F1 with you.
It's been my pleasure.
And as always, keep exploring, keep learning, and keep diving deep into the world of technology. Until next time.